Okay, so let's start the lecture. Our lecture program is starting. So the first lecture, during the first lecture, I will discuss that actually how AI is transforming engineering work. My name is Evgeny Burnaev. I'm Vice President of Skoltech on AI, Head of AI Center. And actually in our center, we work a lot with various engineering problems, and current tools of artificial intelligence are very useful for solving complex engineering problems. And we are developing pipelines, autonomous pipelines to help engineers to solve their problems. And so today I'd like to devote my talk to some aspects of how we can use generative models, multi-agent systems for solving complex engineering tasks. And at the same time, I will start my talk with discussing some theoretical results. Because besides applying tools to problems, it's also very important to understand limitations of these tools and to try to explain why these tools are working. A few words about Skoltech AI Center. In Skoltech AI Center, we have different research directions devoted to large language models, reliability, uncertainty quantification for machine learning models, computational intelligence, remote sensing data processing, applications of AI for physical models, for physical worlds, robotics. In Russia, we are very active in publishing papers at top venues, so we are #1 among Russian universities in this respect. Besides that, we also collaborate a lot with industrial companies and participate in various industrial activities. And our main aim is to make AI a really practical applied tool and help industrial companies to introduce it into business processes. First, I'd like to start my lecture from discussing some foundational aspects of generative modeling. Because although there exist many algorithms for generative modeling, most of these algorithms, actually, we don't have a very good mathematical explanation of why they're working. And this is very important. So as you know, progress in modern generative AI is very, very fast. And maybe you remember that in 2016 or so, the first version of generative adversarial networks were invented. And quality of those results were, of course, better than using standard machine learning methods. And then throughout the years, the quality of generative modeling of such complex data as images improved really significantly. Moreover, nowadays we can control what we are generating, how we modify images, so we can control this by textual commands. These are some results of how we can generate images from text prompts using Sber-Kandinsky model. You see the quality is very good. And as I said, there are, of course, nowadays there are many different variants of generative models. But the two basic approaches are: the first is to construct generator adversarial network. That is, we construct some neural network which maps random noise with some simple distribution into a complex distribution over images. And we train this generator in a game theoretic manner in such a way that it plays with a discriminator to try to fool the discriminator. And the second approach, conceptual approach, I mean, is based also on transforming some simple distribution into complex distribution over some given complex experimental data. But here the transformation is realized through some stochastic process. And the standard, the very first model was based on diffusion processes. So the approach is as follows. We have a distribution of real-world data, and then we start to add noise to this distribution of real-world data step by step. This noising process is governed by a stochastic differential equation. And at the end, the distribution converges to some limiting distribution. Usually it is just Gaussian multidimensional Gaussian distribution. And because in case of stochastic differential equations, we can reverse these stochastic differential equations, then we can do the following. We start simulating these equation in reverse time in such a way that it starts from the limiting Gaussian distribution, but the limiting distribution of this reverse process, it arrives to the initial distribution of the original data. In such a way, we can really model some complex distribution just based on available sample of images. So this is the second conceptual approach, appeared in around 2020. And then, starting from this conceptual approach, there appeared many variants how we can perform this transformation based on some process. There exist other different stochastic processes how to perform this transformation, but also the very last models are mostly based not on stochastic transformation, but they are based on deterministic transformation. And this deterministic transformation is usually called continuous normalizing flows. So we assume that there exists some flow defined by a vector field. This vector field we denote by the function v. And so the flow, which is a multidimensional transformation phi, it is governed by a deterministic differential equation. And this flow v, it governs the trajectory of this state vector phi. And if the thing is, the question is how to construct such velocity field v in such a way that when we simulate the trajectory of this deterministic process, then if it starts from some simple distribution, then the final trajectory at point of time t equal to 1, it should arrive to the distribution which we would like to simulate, the distribution q of x. In practice, of course, we don't know this distribution q of x. We only know some sample from this distribution. And so if somehow we constructed such trajectory phi, then for each moment of time t between 0 and 1, we will have a marginal distribution, which is actually the continuous transformation of the initial density p0. And the question is how to construct such normalizing flow phi in such a way that at moment of time t equal to 1, it arrives to the distribution of interest q of x. So let's assume that there exists the true normalizing flow u and the true normalizing flow u. And if we know it, of course, to reconstruct the flow, we can just we can take some function class for example, given by a class of neural networks, and then we simulate then we approximate the flow U by this neural network by minimizing this function L of theta. Do you understand correctly that you don't see the arrow when I point it on the notebook, right? You don't? No. Yes, correct. Unfortunately. Okay. Okay, then I will use laser pointer. Okay, so let's assume that we know this function U somehow, and then we can take just a neural network to approximate it. Of course, in practice, we don't know the true flow U. And here is the trick which we can use in order to construct the flow which can help us to represent the distribution Q. First of all, we introduce a conditional probability path, PT of x given x1. So x1 is the limiting point, and we assume that x1 is distributed based on the distribution Q of x. If x1 is fixed, then we would like to construct such a conditional probability path such that at the moment of time t equal to 0, this conditional distribution is given by some simple distribution p of x. For example, it is just Gaussian distribution. But then when t goes to t equal to 1, then this conditional distribution should be equal to some Gaussian distribution around the point x1, and the variance of this Gaussian distribution usually we set it to some small value. So it means that this distribution is almost delta function around point x1. So in this case, the marginal probability path Pt of x, it is just an integral, it is just a mixture of all such conditional distributions mixed with the limiting distribution Q of x1. And actually, because this density here, sigma, because it is small, as I said, usually in practice we set it to some small value, then this Pt of x when t is equal to 1 is almost equal to Q of x. It is just a slightly smooth version of Q of x. So these are two limiting conditions, that P0 of x should be equal to P of x, some simple initial distribution, usually we use Gaussian distribution, and the limiting, another limiting condition is that Px given x1 should be equal to Gaussian distribution with some small variance now around point x1. What we can prove with this is that it holds that if ut of x is the true velocity field of the true conditional of the true marginal probability path, so ut is the velocity field of marginal probability path, then ut of x is connected to the velocity field of the conditional probability path according to this equation. Actually, this formula in this red triangle frame, it follows just from the Bayes formula. And this connects the flow, the velocity field for the unconditional field and velocity field for the conditional field. What is important is that in practice, it's possible to calculate these this conditional distribution explicitly, but it's not possible, of course, to calculate this unconditional distribution explicitly because it is a mixture with respect to the distribution Q of X which we don't know. And this really helps us to define the function, to define the loss function which we optimize to train the neural network to simulate velocity field based on a given sample. So we do the following. First of all, we taking into account this relation between the conditional velocity field and unconditional velocity field. We can define the following criterion. This is the conditional flow model criterion, which measures the discrepancy between the conditional velocity field and the neural network which we use to approximate this conditional velocity field. In practice, and I will show you in a minute, it's possible to calculate values of this conditional velocity field utx given x1 based on trajectories of the stochastic process. And in these simulations, x1 will be randomly generated from the given data sample. And what is important is that the gradient of the flow model and the conditional flow model, they coincide. So what I want to say is that this gradient, it's not possible to calculate the gradient of this function, but it's possible to calculate gradient of this function. I will show you in a minute how we can do it. And gradients of the first loss function and of this conditional flow model loss function, they coincide. And this important, actually very simple theoretical result allows us to train parameters of the neural network Vt of x such that it will model the velocity field of the true velocity field. And in this way we can define the flow model to transform distribution P of x into the distribution Q of x of interest. And so here is how we do this. In order to define somehow the so in practice, usually we just define some family of conditional distributions. For example, the simplest possible family is again Gaussian, obviously, with mean value and variance given with by such particular equations. Why we select these equations? Well, the answer is very simple. These are two limiting conditions which we should satisfy. And of course, for functions mu and function sigma, we can use any other parameterization, but this particular parameterization, it works quite well. And for this particular parameterization, we can calculate explicitly the conditional velocity field. It is given by this equation. And obviously, we can simulate values of this conditional velocity field. And based on simulation of these values, we can then calculate the loss function and its gradients. Based on gradients of this velocity of this loss function, we estimate parameters of the neural network which models conditional velocity field, and at the same time it models then conditional velocity field as well. And then we can simulate the transformation by solving this equation here. So this is a brief idea behind the flow models. Actually, there are many other variants, modern variants of flow models nowadays, and this technique is used in many industrial applications to simulate complex images and other complex types of data. But the question is, as you see here, we are using actually very simple equations, very simple distributions to model complex data types such as images. Actually, any image, it is a multi-dimensional vector where each coordinate is some pixel of the image. And if the resolution of images is, for example, 100 by 100 pixels, then the formal dimensionality of such image is 10 to the power 4. And obviously, if the distribution of the true image, for example, is uniform, then due to curse of dimensionality, it is just not possible to model distribution of such data in such high dimensional space. But still, methods for generative modeling of images works. And the question is, why? Why do they work? Actually, a very kind of classical idea is because the so-called manifold hypothesis actually takes place. And what is manifold hypothesis? As I said, real-world data is very high dimensional, for example, images. And if we consider any image as a point in this high dimensional space, then distribution of these points is not uniform. Because of correlations between coordinates of images, these multidimensional points are distributed close terms. Oh, so nice music. Very relaxing. I guess this is a sign of a break, right? By the way, maybe it's okay. That's good. So, what I want to say, each point, this is just a toy example on this screen, motivating what do I mean by saying manifold hypothesis. So you can think about each black point on this image as just an observation. Because between coordinates of each such observation, there are nonlinear correlations. These points corresponding to real-world data, they are distributed non-uniformly. And we assume that there exists some geometrical place of points, which is called usually manifold, such that all observations which correspond to real-world data, they are located close to this geometric space of points, close to this nonlinear surface. And this nonlinear surface, it models on average typical dependencies between coordinates of real-world data. And the thing is that dimensionality of parameterization of such nonlinear surface is significantly smaller than the dimensionality of the space of initial observations. And because of that, actually, we are not working with the full dimensionality, we are working with a smaller dimensionality. And so if different observations here correspond to different images, when we solve problems of classification, of predictive modeling, we should take into account, of course, the geometric properties of this data, how it is distributed in the observational space. And the question is, do conditional flow models really take into account somehow the geometric properties of geometric place of points? So, as I said, a typical model behind this manifold hypothesis is the model of manifold. The simplest, you can think about the simplest manifold as some nonlinear transformation which maps a low-dimensional vector z, which is kind of a low-dimensional parameterization, to a high-dimensional vector x, which is our observations. Possibly there is also some noise, of course. And we assume that all our real-world data is somehow the geometric place of all real-world observations is modeled by this, is defined and can be modeled by some such nonlinear function g, which is of course difficult to identify, but because somehow it exists, the real dimensionality of data is small, and because of that, it's possible to model real-world data even with a very complex structure. And now the question is, do conditional flow models take into account somehow the geometric property of data? And the answer is yes. It's possible to obtain some theoretical results which really demonstrate that such models as conditional flow model, such models take into account geometrical properties of data. So let me return to some previous slide. And in this here, I said that we are approximating the conditional vector field by using some neural network. Of course, if we use a neural network as an approximator, it's very powerful, but it's a bit difficult to perform the analysis. And now I will present you I will present you some theoretical result explaining how conditional flow models take into account geometric structure of data. But this analysis, it is based not on neural networks, but it is based on a simpler regression model. Actually, when we optimize this loss function here, we solve a regression problem, right? Because we approximate function ut by some function v from a given class of functions. In practice, we use neural networks, but to perform theoretical analysis, of course, it is easier to use some simpler approach. And the simpler approach is to use kernel regression, because kernel regression is very easy for theoretical analysis. As you may remember, kernel regression, it means that we have some outputs y, we have some inputs x, and we would like to calculate the conditional expectation of y given x. Actually, this is the best L2 estimator when we predict y given x. And in case of kernel regression, this estimator has a very simple form. This is just a linear combination of values, of known values of y with weights which decays proportionally to the distance, which decays as some kernel function depending on the distance between the point x and points xy from the training sample. So this is the regression model we use. It is easier for theoretical analysis, and it's possible to prove the following bound. Here I don't, of course, introduce all these notations, all these theoretical details. It's not important now. I just want to explain what kind of theoretical results in this respect we can get. Tau here, it is a parameter. It is called the reach or curvature radius of the data manifold. You can think about the bigger tau is, the less curved your manifold is, and vice versa. And what we can prove is the following. Let's assume that we construct a conditional flow model when we use some simple kernel regression to approximate the function v. This is the first version. And using this simple regression, we reconstruct the velocity field, and then we construct the generative model which maps one distribution into another. Then we use the same kernel regression, but this kernel regression takes into account the structure of the manifold close to which our data is located. By saying structure of the manifold, I mean we take into account the tangent space to the manifold. Tangent space in the sense that for each point on the manifold we can have some tangent subspace and of course the normal subspace. And so if we know this tangent space, we can estimate the geometric place of points more accurately, obviously, but in practice we don't know the manifold, we don't know its tangent space, and this is kind of an oracle. And so let's assume that this distribution is the distribution given by the generative model in which we use a simple kernel function, and this is the distribution of the data which we obtain when we use the kernel function, inside which we take into account the tangent space of the manifold for each point where we perform simulations. In other words, inside this kernel function here, inside this kernel function here, we also introduce the tangent space so that the kernel function adapts to the tangent space of the manifold. As I said, in practice we don't know it, but this is kind of an oracle. And the statement is that the distribution of such oracle and distribution of the generative model without knowing the tangent space, they're quite close. What is it? Ah, yeah, I guess this is a break, right? End of the break now. Okay. I remember my childhood, and my childhood, it was not such pleasant music. It was like some ring, very nasty ring. And so this is, of course, better. So let's wait a little bit. Okay, that's good. So what I want to say is that the distribution of the generative model, which takes into account the geometric structure of the manifold, and the distribution of the generative model which doesn't take the structure of the manifold into account through this oracle, they're close. In this, of course, this bound depends on the curvature of the manifold, and if the manifold is very, very curvy, it means that tau is very, very small, the bound is not very good. But still, if the manifold is not has quite big reach, then the difference between these two distributions is not that big, and this is one of possible explanations, indications that a generative model automatically adapts to the tangent space of the manifold. It's also to prove another statement about conditional flow models. This statement is as follows. If for each point of the manifold we have the normal subspace and tangent subspace, then the closer to manifold our trajectory of the conditional flow model is, the norm of the projection of the trajectory on to the tangent space, it goes to 0, and the norm of the projection of the trajectory to the normal to the manifold, it increases compared to the norm of the projection on the tangent space. In other words, it means that the closer to the manifold the trajectory is, the direction of the trajectory is kind of, it coincides with the normal to the manifold. It is another indication, and I hope soon we will publish a paper with these theoretical results. But what do these results mean? They mean that such models as conditional flow models and other other such models, they automatically adapt to the geometric space, geometric properties of data distribution. And this is one of qualitative explanations why such generative models work in practice, even for such high-dimensional data as images. So as you see, it's very important to analyze properties of generative models, and still there are many questions why they really work so efficient. And this small result is just one of possible explanations, but it helps us to understand how they work. Okay. Now let's discuss how such models, how such generative models can be introduced in industrial practice. There exists so-called paradox of AI implementation. According to McKinsey research, in most organizations, AI remains at the pilot stage, and actually a lot of respondents are already experiencing at scale AI agents, but for them it's very difficult to estimate economic, efficiency of such AI agents, and they don't know how to evaluate, how to control, how to manage AI agents. And one of the barriers of this problem is because of always there is more fundamental stuff, algorithms, models, and there is more production stuff when these algorithms, models should be somehow introduced into practice. And this intermediate layer, in many cases for multi-agent systems based on generative models, this intermediate layer, which helps us to evaluate multi-agent systems, to control multi-agent systems, to manage AI agents, the layer is absent. And actually, we thought about this already some years ago, and we called this intermediate layer as engineering AI. And let me explain how we think about how to construct this intermediate layer. So engineering AI, of course, it's not AGI, but it is already not a narrow AI, which is usually used to solve such simple tasks as classification, semantic segmentation, predictive models. We actually came to this concept when we were solving many industrial tasks, such as tasks in oil and gas, in processing of documents, and one of examples of such complex tasks is so-called self-learning reservoir model. Actually, let me explain what is the industrial use case behind this model. When we model a oil and gas deposit, we have to process different types of data. Seismic data, hydrodynamic data, data of geological data. These are very different types of data with different locality, with different accuracy. And based on this data, we have to obtain kind of integral estimates of different properties of oil and gas reservoir across the whole reservoir. And for example, seismic data is very inaccurate, but it gives you information about the whole reservoir. And say data of geological studies, it is very local, only near particular holes in the oil and gas reservoir, but at the same time it's very accurate. And so based on this data, we have to obtain estimates across the whole reservoir, estimates of porosity, permeability, other characteristics. Based on these characteristics, we have to predict oil production. And then we compare this oil production with real oil production, and then we have somehow to tune these estimates across the whole oil and gas reservoir. But the whole oil and gas reservoir model is very, very complex. It is a three-dimensional distribution of different physical characteristics. And it's very difficult to tune these three-dimensional characteristics across the whole reservoir in a consistent manner. in such a way that you keep all the physical properties consistent with each other. You take into account physical equations. You should preserve various physical invariants. And to solve this problem, we developed the following concept. We, first of all, we constructed a knowledge graph, which actually it explains all possible operations which you can do with this type of data. How to transform one type of data into another type of data, which solver you should use for that, which equation you should use for that. Based on this knowledge graph, we actually can plan any calculations, any simulations to simulate any properties of the oil and gas reservoir. Then we construct an orchestrator which takes the available data about oil and gas reservoir, and then it plans the computational pipeline based on a knowledge graph. In each step of this pipeline, and each step of this pipeline, it is based on a particular solver or on a particular physical equation. And as you can understand, this is actually some particular instance of multi-agent system, right? And at that moment, we realized that many of the engineering problems, it was like maybe already 4 years ago, we realized that many engineering problems of such type can be realized as a multi-agent system. And some of the agents in that multi-agent system, they should be, of course, based on generative models. And these generative models should be fine-tuned not on image data or on other typical types of data, but it should be fine-tuned on special types of data, such as seismic data, geological data, say CAD data. Later, I will talk about a little bit about computer-aided design data, which is usually used to describe mechanical parts or buildings, so 3D world around us. And so, using such generative models fine-tuned on these special types of data, we can, for example, data of geological studies, of hydrodynamic studies, of seismic data, we can perform conditional simulations of physical quantities of interest given our observations. And such agent, it can give a preliminary estimate of the whole oil and gas reservoir, and then the multi-agent system starts to modify these estimates to perform better alignment of the predicted oil production with the true oil production. So this was for us a motivation that multi-agent systems is the next step in engineering design, because orchestrator, it interprets the problem of the user into the sequence of steps based on subject domain knowledge, and then it plans computations. It runs different solvers, or it runs different generative models, obtain the result, and then repeat the cycle in case the results are not fully convincing, if they don't meet user requirements. In this respect, it's also very important somehow to keep knowledge about subject domain, and we started working on how we can represent memory for agents. And one of simulation environments where it is very useful to test different types of memories is of course game environments, environment with games, because games for us, for people, is a very good thing to train our physical abilities, to train our mental abilities, to train different aspects of these abilities. And we also decided to test different approaches for representing memory using games, in particular text-based games, because obviously the orchestrator, it is based on language models, generative language models. Actually, text-based games, this is the these are games from 90s. When you have a very simple interface, you on each step you get some information about the environment. You plan your action, you get the feedback, and then you repeat. There exist different types of games like cooking, like I don't remember exactly. So these are games where you should travel from one room to another and collect items, perform some actions with these items. And what is important, because there are many steps, it's very difficult to remember what has happened on previous steps, even for a human, even for a professional gamer. And so if you use a standard large language model, even with a large context, very soon this context will the context of the language model will not be able to follow all the steps, and very soon the large language model which plays such game, it will fail. So we decided that the memory should be external, and obviously it should be represented as a knowledge graph. This idea was based both on our engineering experience from those engineering problems, and I like the one about oil and gas, and also because we are working with texts. Well, knowledge graph concept is a very convenient way to represent the memory. So we structured the memory into two types: episodic memory and semantic memory. It means that on each step of the game, when the agent gets into the room, it gets some information about the room. Then large language model, agent based on the large language model, it represents this information about the room in the form of triplets. And also these triplets are grouped into episodic events. And so we get a knowledge graph which contains both semantic vertices, and the groups of these semantic vertices, they are combined as episodic events. Because and each episode it is connected with a particular situation in the game. For example, in this figure, it means that the agent gets into the garden where the agent found apples, and this is an episode. So based on this memory, which actually we construct this memory on the fly. So as soon as we get information about new level, we reconstruct the knowledge graph, we update it, we add new vertices and remove old vertices. And then based on this information, we plan our next action using kind of standard technique, not so important now. What we achieved that it's possible to play these text-based games very efficiently. So even if we compete with kind of a professional player, the performance of a professional player and the performance of such multi-agent system doesn't differ too much. And of course, if we compare with all different reinforcement learning based agents or agents based on long context or agents based on retrieval augmented generation, their performance is not so good. And this is an indication that representing memory as a knowledge graph with a specific structure is very efficient. Since then, there were many other papers of such type how to represent external memory. And we, at some point, we arrived to the concept of engineering AI, which should be a multi-agent system with orchestrator, with a library of agents, such that based on the user problem and available data, the orchestrator decomposes the problem. It selects the pipeline based on agents and knowledge from the knowledge domain, and then it performs simulations, and based on the results of simulations it can continue transforming the computational pipeline or stops and provides the result to the user. And actually we elaborated this concept some years ago. And at that moment, people started working with multi-agent, only started working with multi-agent systems. And now we are developing our multi-agent AI engineering platform for complex engineering solutions. This platform can work into two modes. The first mode is ready-made product systems. It means that for some typical engineering tasks, we already predefined the pipeline, the workflow. We composed it from the available agents, and the user gets some interface and provides data to that interface and get the results. So very simple. The second part is fully adaptive. It means that the user provides available information, available data about the problem. Orchestrator decomposes the problem into sub-problems, plan the solution based on agents, and it can repeat this step as many times as needed, given the computational resources, and then provides the result to the user. So unfortunately, this is some simulated movie. Unfortunately, the interfaces are in Russian, but I guess you can understand the concept. So the orchestrator selects those agents which should be used for the given problem. It runs the computational pipeline and returns the results to the user. So very simple concept, but it works with current language models very efficiently. What is important here is that for engineering problems, it's not possible to use standard agents from available libraries, standard language models, because engineering problems are far more complex than just document processing. We need many different specific agents to solve real-world problems. Here are some examples of such agents. For example, if we deal with data from sensors or with transactions, it's important to have efficient generative models for such sequential data. It's important to have good external memory, as I said. And when we perform predictions of some effects, it's important to identify the main factors which influence the metric of interest, right? And so causality analysis is the only tool which allows to do that. And now let me briefly overview of the types of engines we are developing. For example, generative modeling of sequential data, and Alexander Korotin, he will be delivering talks on how to construct generative models using modern methods of optimal transport and diffusion processes. Why diffusion processes are nowadays popular for sequential data? It's because we can generate sequential data not token by token, but we can generate a significant a long sequence of tokens after several iterations at once, and so this helps us to reduce computational costs and control better dependency between the subsequent tokens in the generated sequence. And in this case, we achieved, in this direction, we achieved good results. So Alexander Korotin will tell you about this and other such kind of approaches. Causality. Well, causality is a very important tool nowadays, because if you predict complex phenomena, if you would like to, for example, understand which variables are the key reasons and which variables really influence the, say, your profit, you need first to identify the causality graph. And in this research direction, we constructed some parallel algorithms. Let me explain you why do we need parallel algorithms here. Actually, most of classical methods for reconstructing such graphs, causality graphs, they are very time consuming. And it may take like 10 hours or even more if you have many variables and you would like to estimate causality graph between these variables, right? So we developed parallel versions of classical causality analysis algorithms, and this allowed us to significantly accelerate these algorithms. And why this is very useful? It's useful because we can run these algorithms in parallel based on subsets of variables. We will get different causality graphs. And then we can really improve accuracy significantly using a simple voting. So because we get an ensemble of graphs, of causality graphs, we use simple voting procedure to vote whether this edge between variables is really needed or not. And it turned out that even such simple recipe helps to improve accuracy of causality prediction very significantly. And this resulted in a significant improvement of the downstream predictive models. And this is all thanks to the parallelization of causality algorithms. Also, as I said, it's very important for multi-agent systems to have external memory, efficient external memory, and that idea with knowledge graphs, external memories, knowledge graphs, we are continuing to develop it. So we demonstrated that if we construct the knowledge graph on the fly, take into account whether the event we extracted, whether this event is new or old, so we take into account temporal components. It's possible to improve up to 15–20% with respect to exact match metric in QA pipelines compared to state-of-the-art RAG techniques, both graph RAG and standard RAG. And this means that this approach for composing the external memory is very important. As you see here, I'm just explaining. So what I want to say? I want to say that for real engineering problems, it's very important not only to use standard agents, but also some of the agents should be very specific. Some agents should be based on physical models, on some solvers. Some agents should be based on such specific techniques of machine learning like causality analysis. But in some cases, you may not have a necessary agent in your library. And in this case, you need some meta-learning technique that will automatically generate an agent for you. And in a minute, I will briefly overview some approaches for autonomous agent construction, which we call it agent creator, and how we can perform scalable creation of self-learning agents in case we don't have the agent in the library if we need some specific agent and we don't have it in the library, we can generate it autonomously. Of course, it's very important to have different cognitive architectures in the system. So we are developing different cognitive architectures based on decision trees, based on other approaches. This is a particular example of such cognitive architecture. This is an instance of the architecture we used for helping sales managers of a bank to allocate requests of users. Okay. I think I'll stop discussing this multi-agent system at this point. And what could be the next steps? Actually, people already started thinking how to transform this multi-agent concept further. And one of the concepts which is nowadays considered in the literature is so-called it is so-called a Hayes paradigm. In other words, this is AI hyper-agile software development based on model-based system engineering. Well, what is written here could be a little bit not so easy to understand. But let me explain in a very simple terms. When you develop a software, you usually use different principles how to develop software which is reliable, how to control bugs in your software. And these principles are patterns for decomposition of software when you develop the software. These are various UML diagrams. After each cycle of software development, you have to develop specific documentation, specific unit tests, and modern coding agents and systems for coding. They just don't take into account that these development patterns into account. They are not introduced inside the modern coding agents. And this paradigm, a Hayes paradigm, means that these patterns of how you develop software, they should be integrated inside the coding agents. And the same thing is actually valid for engineering, because when you design engineering systems, you also use the same similar patterns. And this is a very important thing as a next step. Now, let me briefly overview self-learning agentic systems with skill and tool generation, and briefly present some particular industrial use cases. Concerning the autonomous systems for developing agents. All of them can be classified into several chunks. The first, of course, are chatbots such as ChatGPT, DeepSeek, and others. The second are so-called co-pilots. So these are systems that help you. And then advanced tool agents such as OpenClaw, which are integrated on your personal PC and helps to work with, helps to perform some daily tasks. But actually, in many cases, it's important not only to assist, but also to develop agents in an autonomous way. if you have some specific problems for which you have to develop agents and reuse these agents, then we need a tool that, given your problem, can create a reusable agent. And this is what is missing, actually. And we developed a capability which helps to perform the following pipeline. So we have some textual task. The system decomposes this task, generate code, texts, and fixes. And then it generates the working agent, including a large language model if needed. And this agent can be reused many times for a similar task. What is important is that while creating such agent, we can also combine different trajectories of solving a problem and combine them in a separate skill. And this skill also can be optimized and collected inside the library of skills. And this really helps to improve efficiency of the pipeline. So the system extracts successful experience from logs and form reusable skills. And then these skills can be reused when you solve other problems. Okay, I think I'll skip. Here is a demonstration how this works. So you define your problem. The system starts solving it, and then at the end it generates the code for a particular agent and some documentation for this agent, and then you can reuse this agent many times for similar problems. And here is here is an example of such problem. Let's imagine that we would like to download on a regular basis some movies from YouTube. And for each of such movie, we would like to extract sound and then convert the sound into text, extract some meaning of the text, and summarize it. And the system in this case, it will develop the code which will do all the steps for any given movie you want. And then you can integrate this agent into any pipeline in your multi-agent system. And so this agent creator can be used for creating agents when you don't have a particular agent for a particular step in your multi-agent system. What is interesting is that if we collect traces of creating different agents. Actually, when you create an agent, you solve a problem. So you collect traces, and then you form a new skills from these traces, and then you can optimize the skills. As we demonstrated on different multi-agent benchmarks, this really improves efficiency significantly, up to 30-45 points on key metrics such as accuracy of problem solution. And the more cycles of skills optimization we use, the better the efficiency of problem solutions increases, as it follows from these plots. And what is important is that if we collect more skills, then the number of tokens which we use for solving new tasks, it decreases. And so this means that during solution of different problems, the system adapts to such problems by collecting different and optimizing different skills. So that's it about engineering AI and multi-agent systems. And just to summarize, nowadays we have all necessary tools to develop autonomous systems that can decompose your problem, take into account subject domain knowledge from the external memory, for example, from the knowledge graph. And if some new agent is needed, the system can even create it and introduce in the computational pipeline. And then the orchestrator run that computational pipeline, get the result, and if needed, it can correct it. While solving different such problems, you can collect trajectories of solution, distill it into skills, optimize the skills, and collect the skills such that your problem will, such that your system will perform better because the more you solve the problems, the more skills you collect. And these skills help you to solve the problems and decrease the number of tokens you use. And now let me briefly overview, just maybe in 5 minutes, not more, some particular industrial use cases we solve by using such kind of multi-agent systems and computational pipelines. For example, the problem of analysis of technical documentation for construction facilities. When you perform construction of some facility, it's very important to check that your design, your scheme, it fulfills particular requirements. These requirements are given in a very big documents of technical requirements. It's not so easy to understand which of the requirements are fulfilled, which not. And what we can do is to use large language model and such multi-agent systems to extract requirements from technical documentation, represent them in a machine-readable format when we have subject, another subject, some relation between them. For example, that this electric line, it should be not 3 meters closer to this wall. This kind of representation of technical requirements, and then we check whether these requirements really are fulfilled in your construction plan. Using such multi-agent systems, we can develop we can develop computation pipelines to generate building information management data, which represents complex buildings. We can solve the problem of reverse engineering. It means that we have some 3D dimensional scan, and then we we generate a BIM model which is in line with this scan. And this helps us to actually automates the reverse engineering problem. We can solve the problem of review of two-dimensional drawings and schemes. Such kind of schemes, it's very difficult to review it, to check that this scheme fulfills all the technical requirements from the documentation. And the only possibility is to use visual language models and multi-agent systems based on them to extract different elements from these technical drawings and check whether these elements fulfill the requirements. As you can understand, in engineering there are many such type of problems, and when you represent this solution to these problems as multi-agent systems, then it really helps to perform the level automation and get rid of various errors. And the last but not the very least, when we are dealing with engineering objects, it's very important to collect three-dimensional information about such objects. So we are working on various 3D scanning technologies and shape reconstruction. Based on this data, we constructed an agent that can work with complex 3D geometries. The idea behind this agent is that engineer presents some textual description of the 3D shape. Possibly it gives also some images of the shape the engineer wants to reconstructs. And then our system should return the engineer computer-aided design geometry, CAD geometry. And this is a very special. This is a special format that can be converted into different other formats. Some of them are even suitable for printing, so you can just print this 3D shape. And in this, to solve this problem, we constructed a system based on language model, because actually any 3D shape, any CAD model, it can be represented as a computer code. And this code can be executed so that a special engine generates a 3D shape out of this code. And what we did, we fine-tuned a language model with several decoders, visual decoder, tokenizer, which can process CAD code, and tokenizer which process textual data. And this language model, it can generate CAD 3D shape, given textual description, and given images or point clouds, so that you condition your generation based on this data. And we demonstrated that, of course, such kind of systems already existed, but in our case, we were able to increase complexity of such generations significantly, complexity and accuracy. And this is an example of some competing approach, and you see that the generation of the mechanical 3D shape is not good, because the reference 3D shape is like this, and our generation is accurate, and it corresponds to the ground truth. So, as a conclusion, as you see, the mechanisms underlying generative models should be investigated, because we would like the artificial intelligence to be explainable, to be reliable, and the only thing the only thing how we can do this is to really understand in a mathematical way how such models work, how such generative models work. And so today I presented you some particular results of about how generative models of continuous data take into account geometrical structure of real-world distributions. We can compose multi-agent systems based on such generative models and other subject domain models. And these multi-agent systems can solve complex engineering tasks in an automatic, autonomous way. Actually, this is the next step in engineering automation, and I'm sure that very soon there will be various engineering systems exactly based on this concept. Already, such big companies as Dassault Systems, Autodesk, they are going in this way. They are developing such kind of capabilities for their engineering problems, and this is the important next step. Thank you. Okay, as I promised, I didn't use the whole time I have. So if you are not tired too much, we have some time for questions.
Thank you for your presentation. At the very beginning of the presentation, you overused some contemporary methods of flow-based models and manifold theory. How does these methods handle conditional generation? And does this problem with the generation of conditional data with a manifold while training on lower dimensions?
I'm sorry, it's because of echo, it's not so easy, maybe. Раз. Так. Так, а как мы... А может maybe you can come here and just ask a question here, because to be honest, if you use that microphone, not so easy to understand because of the echo. So you said that, okay, I'm using manifold.
Yeah, you told that you describe overview of flow-based methods and manifold theory, and what is the contemporary methods for handling conditional generation with the help of flow-based methods and manifold? Because while training on manifold, we are using a lower dimension, as I understand.
No. Actually, let me reiterate. What I said is that if your data is located near a manifold, then the conditional flow model can take properties of that manifold into account automatically. And this is one of possible explanations why conditional flow models can work with high-dimensional real-world data. We assume that for high-dimensional real-world data, this manifold hypothesis is true, and there are many papers that experimentally confirm it. And these theoretical results demonstrate that this type of models take properties of the manifold into account automatically. And actually, this result that can be generalized not only for conditional flow models, but also for other type of models as well. There exist so-called stochastic interpolations, stochastic interplans, and stochastic interplans is a generalization which includes all possible models like diffusions, kind of flow models, whatever, Schrödinger bridges, and this kind of statement can be proved for stochastic interplans actually. Other questions?
Just works. Thank you for the lecture. I wanted to ask you about the project with the self-learning reservoir model. Which type of data did you use to carry out this research, and why is it particularly self-learning?
Okay, so for any reservoir, the typical data provided by a company, by oil and gas company, is a seismic data, which tells you on average where the porosity, where the permeability is close to zero, or where the permeability is not close to zero. So where the liquid can flow and where the liquid cannot flow. But this information is very imprecise. But it's about all oil and gas reservoir. And also you know information about geological studies and information about hydrodynamic studies. But this information is very local and it is available only close to particular wells. And this information correlates with porosity and permeability. And so you see that you have different types of data. Some of the data is precise but local. Some of the data is imprecise but about all oil and gas reservoir. You would like to estimate this porosity, permeability, and other characteristics to predict oil production over the whole oil and gas reservoir, and to plan where you have to construct a new well. And this is the type of data we work with. Concerning why this model is called self-learning is because okay, the user provides some particular information about the oil and gas reservoir, and then the orchestrator automatically constructs the pipeline. So depending on the available data, it selects which computational tools to use and how to process available data. Then it predicts soil production, and if it doesn't coincide with the true oil production, then it starts to evolve the structure of the computational pipeline. It starts to fine-tune hyperparameters of the computation pipeline, so in order to decrease the discrepancy between predicted oil production and the ground truth oil production. In this way, we can fine-tune the whole oil and gas reservoir model, so that the prediction of oil production is more or less accurate. And this kind of self-evolution. So you just provide the available data, you provide domain knowledge about the oil and gas reservoir you have, and then the orchestrator starts the process of model construction in an autonomous way by self-evolving. Other questions?
Hello. Thank you for the lecture. It's quite interesting. I would like to know, like, does Skoltech is working on any kind of application of AI and ML for biomedical research or in agriculture? Because as I see that you guys are working mainly on engineering tasks or for like oil and gas fields. So
okay, well, yes, of course, we work on, first of all, in this school there will be several lectures on biomedical applications. And of course, in Skoltech, we're working on this topic as well. We have several groups, computational imaging for biomedical applications. We have a research group which is working with analysis of computer tomography, MRI, functional MRI data. Yes, that's true. And engineering domain is just my personal kind of domain of interest. That is why I presented you today many of such kind of examples. But it's not the only domain we are working with. Other questions? Yes, please.
Thank you for the lecture. It was interesting. My question is about an agent with an innovative memory structure, and my question is which possible application you see beside games, and if it's possible to use these agents for data analysis, maybe.
Yes, of course. Actually, games was just a it was just a playground to test ideas. It's very maybe you remember one of the very first reinforcement learning models, deep Q network, were invented exactly as the agent to play Atari games. But of course, nowadays, this deep Q network is used in many real-world business applications. But initially, it was developed based on Atari games, because Atari games is a kind of sufficiently complex, but very easy to use playground where you can test your ideas. And so, in the same, because of the same reasons, we used textual games to check how different types of external memory can be used and which of them are sufficiently efficient as external memory for agents. As you can see from engineering examples I presented at the end of my presentation, there are many real-world applications for multi-agent systems. Other questions? No questions. Okay, thank you for listening. That's it for today, and from my side. And I guess now, what? Right here. Okay.